I'm Leroy Westerling. I'm a professor here at UC Merced, and I've been working on all 4 and now 5 of the state climate assessments.
Awesome. Nancy?
Hi, I'm Nancy Thomas. Thanks everybody for joining us today. This is wonderful. And thanks to Leroy and David and Owen for joining us in this webinar. So I'm the Executive Director of the Geospatial Innovation Facility at UC Berkeley and also the Program Manager for CalAdapt. So thanks for joining us.
Awesome. Owen?
Hi, I'm Owen Duarte. I'm a climate scientist with Eagle Rock Analytics, and I am the science lead for the CalAdapt team and a contributor to the first working group of the Pyregence consortium. So I'm very happy to be here wearing multiple hats, and thank you all for coming today.
And last but not least, David.
Hi, guys. I'm David Saw. I'm a professor at the University of San Francisco. I'm also a principal in Spatial Informatics Group. It's an environmental think tank that's taking the lead for implementing the Pyregence program or project, where I'm the lead PI on that, and looking forward to the conversation.
Sounds good. We'll start with Leroy offering an overview of wildfire modeling that informed the California 4th climate change assessment. Intermittently throughout our session this afternoon, you'll have the chance to ask questions. As questions are coming up, you can feel free to put them in the chat. And with that, Leroy, I'll turn it over to you.
Thank you very much. So I have 15 minutes now and for this first part of the presentation. Welcome, everyone. It's a pleasure to be here. Let me just shrink or try to shrink. Everybody's little videos are covering my screen. All right. There we go. All right. So it's a pleasure to be here. I'll just dive right in. I want to start by motivating this a little bit. We talk a lot in very general terms about why we need things like these assessments, but I want to focus on some very specific concepts. When we are building long-lived systems that provide goods that depend on ecosystem services, like for example, a dam or a city, right? We are relying on a basic concept of stationarity, and that is that we know something about the distribution, the probability distribution of events that can occur, and that while there may be extremes from time to time, they'll come back to some long-term average, like I'm depicting here. So I've got a typical sort of zoom in on some climate spaghetti, and I have a horizontal bar there in the middle that's representing this idea of a long-term average that you return to. And when you're managing around a system like this, you can only afford to manage away or invest in systems that are robust to risks up to a certain point, and then you live with the small probability of high impact extremes that you can't eliminate your vulnerability to over time. But the validity of this sort of conceptual model really depends on those systems being somewhat stationary. In other words, for the life of the investment, the assumptions you're making about those extreme probabilities are correct. In this particular case, that climate spaghetti I was showing you is actual climate spaghetti, not from California, but from the Rockies. And it was temperature, which is a key variable that drives wildfire. And you see that black line there, zigzagging up and down before 2000. That was the historical temperature record that we were using to calibrate our models. And the other colors there are the selection of projections. And note that by the time you get out into the latter part of the century, the coldest year in the future is hotter than the hottest year in history in that location. And that's true in a lot of places. And now if we're talking about modeling fire that's very responsive to temperature, we have these basic problems of how do we model it when it moves outside that historic frame of reference. And we can see some of the impacts here in California. Here I'm showing not the annual area burned in the state, but the largest fire reported each year. And then in 2020, I'm showing the current area burn totals for the 5 largest fires. And notice that one of them is over 1 million acres and far exceeds what's happening in the rest of the state in the previous decades. But also, there's 4 other fires burning that are larger than all but the most recent record breaker before this in 2018, the Mendocino complex. And this has implications for how we did our modeling in the 4th assessment, for example. So when we're thinking about how to provide guidance to people now that we're moving out of this non-stationary world, we still have to make assumptions about how our models respond outside of that historic frame of reference. So in particular, one assumption that we made is that fires would have a maximum size, right? So we couldn't just let them be as big as they might want to be on the landscape. And so we used those fires that you see there in 2012 and 2013, which were the largest at that time. And then when they were exceeded by the Mendocino fire, we said, hey, we're going to be under predicting, right? And now, of course, we've seen a fire that's maybe 3 times the size or more, larger than 3 times the size of what we were using as a maximum. So those are the kinds of judgments that are difficult to justify one way or another. Another aspect of the changing fire regime is that the fire season is getting longer, and the dynamics that come into play, say, in increases in fire very late in the season, can be quite different from what governed most of the fires in the record that we had to work with to estimate our models. So putting aside those caveats for a moment until we start talking about the 5th assessment, let's look at what sorts of products we had for the 4th assessment. We had millions of maps like those on the left that are showing simulations of individual extreme fire events around the state. Those 2 maps stacked on top of each other have the same background probability of a large fire occurring. So those are just 2 different random draws from that same scenario. And when you aggregate thousands of those together, you get something like what you see on the right-hand side, which is kind of like a heat map showing where fire activity is likely to occur in the future, averaged out over a lot of different realizations of a scenario and over multiple years of it as well. And then you can compare the historic situation. So for example, the upper left hand, there are 2 future scenarios like the 3 I've shown here, and there are many more. These are all 3 different climate models with varying degrees of precipitation variability during a specific 30-year period, interacting with similar sorts of temperature trends by that point. And we also have to think about other types of drivers of scenarios, not just climate factors, but say vegetation for another example. And here's sort of a depiction of 2 different pathways, right? On the left versus the right, an ecosystem where we've kept the forest cover more open and the fuel loads down, and it fosters a more sustainable type of fire. While on the right-hand side, we get these big high severity fires that blow out a watershed. And those kinds of considerations were also built into some of the scenarios we looked at in past assessments. So here's some different fuels treatment scenarios for the Sierra Nevada that were contributed by the U.S. Forest Service to the modeling that we did. And looking at those types of fuel scenarios from the Forest Service interacting with climate change by different dates, we get maps like this where we can see the impact of climate in the different time periods, say from mid-century versus late century, versus what fraction of those fuels we were assuming could be treated by specific dates, and their impact on area burned. We also have the problem, the possibility of integrating our models. So taking a statistical fire model and integrating it with a dynamic vegetation model to understand how feedbacks from changing fuels after, say, a large fire combined with a different climate trajectory might feed back in and alter fire risk sort of cyclically going forward. And here is a example of results where we've done that over the Sierra Nevada. So linking statistical fire models from previous climate assessments to dynamic vegetation model with its own fire component in it. It's the Landis 2.0 model. And so those dashed lines and the variability in shaded area around them are showing the fire trajectories on the left-hand side for transects through the northern, central, and southern Sierra, where the vegetation is assumed to be static in the sense that the fire model doesn't get feedback from the dynamic vegetation model. And then the solid lines and the shaded areas around them are showing scenarios where we do make that link, and the changing fuels feed back into the statistical fire models assessment of the next time steps risk of fire. And you can see that when we do that, we get less area burned by the end of the century in those different locations than we would have if fuels had stayed the same. And it's not depicted here, but a big part of that is smaller maximum fire sizes and lower fire severity. And then on the right-hand side, you see the impact of those differences in the modeling on the total carbon held in the ecosystem. It's a much smaller impact than is the change in area burned, because the reason you're getting less area burned is that you have less fuel available to burn by the end of the century. But still, there's a difference there that we can identify in the model. And so we can do other things, like we can look at the pace of fuels management implementations on the landscape and their impact on the stability of carbon reservoirs by being able to integrate these two different approaches to modeling. And we also can work with communities around the state, for example. So here on the far left, you see some individual simulation outputs in the San Mateo County vicinity. And in the middle panel there is an average by end of century of the area burned projections, area burned simulations over a set of climate models. And they had a common feature that after the 2050 or so, it very frequently has this red spot right there over the northern Santa Cruz and southwestern San Mateo counties, where there's a big increase in fire projected. And we wanted to map these at finer scale for communities there to work with for different planning scenarios. So on the far right there, you see sort of hypothetical fire perimeters that were drawn, working interactively with fire managers and emergency managers and county staff. And the largest of those at the bottom, that's we called that the San Gregorio scenario. So each of these fires had a storyline around it, and where it would start and how it progressed. And that was a fairly large fire, just under 100,000 acres. And then we used our library of scenarios developed for all the different climate models and population projections and global emissions scenarios and what have you, to estimate frequencies of these different fire sizes occurring. So we could put not exactly a probability on it, but an expectation based on the modeling assumptions. And the second to last row there, you see the San Gregorio, that larger scenario. Even by the end of century, we're saying, hey, this is less than 1% probability of occurring per year in a simulation in general. But it's important to note that we don't incorporate in our modeling some aspects of interannual variability that can be quite important. Like, for example, clustered dry lightning strikes, right? So that's not something that is explicitly in the model. And in the fourth climate assessment, we also didn't have things like wind speed and direction and relative humidity from the climate models at fine spatial scales that we could use to look at changing fire risk and the interaction between things like lightning strike variability or precipitation variability and temperature. And people thought that those outcomes were still quite unlikely, but now here I'm showing you this year's CZU complex perimeter, just over 86,000 acres. So it's a little bit smaller than our worst case fire in terms of area burned, but basically in the same place, starting in the same location as what we had storyboarded out. It didn't get quite as far north into San Mateo County, especially developed areas of San Mateo County, as what we had mapped by hand, but very similar fire. So I will stop here and end my screen share. And I think we're right. We got like 1 minute left before the end of our 15 minutes.
Thank you, Leroy. The data that Leroy has just presented, the modeling effort is hosted on CalAdapt. And so at this point, I'd like to turn it over to Nancy from the CalAdapt team to highlight how you can access this information through the CalAdapt platform. And then we'll take a break for some questions directed toward both Leroy and Nancy. So if you've got any burning inquiries, feel free to put them in chat and we can bring those up during our Q&A session. So with that, Nancy, I'll turn it over to you.
Great, thank you. Let me just share my screen. Okay. All right, do you see CalAdapt?
Good to go.
All right, great, thank you so much. Thanks everybody for joining us today, and thanks Leroy, Dr. Westerling, for the great introduction to the wildfire projection work that you've done for California's fourth climate change assessment. So I'm going to introduce the wildfire tool on CalAdapt, which allows you to explore the data that Dr. Westerling has been talking about. And I'm also going to go over several different options that we have for downloading the data. So if you're interested in doing further analysis or customization, there's a lot of different ways to access the data. So with CalAdapt, I'm going to just go directly to the wildfire tool. And this, as we learned from Dr. Westerling, there's many different variables that are considered in the wildfire modeling data. So this is actually one of our more complex tools that we have on CalAdapt. So I'm going to walk you through the major features of the tool, and then we're going to explore a particular area of interest. So just to walk you through what the tool is doing on CalAdapt, up at the top, we have our user controls. And we'll go through each of these a little bit. The very first thing that you can do as a user is choose to either look at the area burned. So this is the data directly coming out of the UC Merced wildfire modeling that's looking at an annual average acreage burned per pixel and per area. We also have done some additional modeling with that data to create decadal fire probability maps. Those are looking at the probability that there will be one or more fire within a grid cell during a decade. So that was created using the full range of simulations for each model emission scenario and population growth scenario. So that's something we can look into a little bit also. As a user, you can look at either annual or monthly data. There are 3 different population growth scenarios that were used in the wildfire projections, so you can choose which of those to look at. As with all of our CalAdapt tools, we look at 2 RCP scenarios, so the medium 4.5 or the high emissions 8.5, so you can choose those. And then you can always aggregate over different boundary layers depending on what you're interested in. Another thing that I want to point out with our wildfire tool is that we have been developing this take a tour guide that helps you to walk through the tool. So if you come back in the future and you're a little confused about what you can do, check out this tour. I think that should be really helpful for new users to understand the amount of data that we're showing here. So with that, I'm going to move down and talk a little bit about the animated map and then the charting that we can use to really explore this data. Actually, before I do that, I want to also scroll down. As most CalAdapt users know, at the bottom of all of our tools, we link to the actual data set that we're using. So you can see the UC Merced data set. We link to Dr. Westerling's fourth assessment paper. So you can see that as well. Oh no, where is it? Sorry, can't see my screen to get back. We also describe the additional processing that we did on the derived products. For the probabilities, we used a methodology that was also in California's fourth assessment. You can look at the Dale 2018 paper for more information about that methodology. So those links are always at the bottom of the tools if you want to learn more about the data. So looking at the way that our map and our time series interact, we can click on any pixel in the state and we get the time series chart of, again, average area burned. And we can look at this chart either by decade, or we can actually look at the annual results. I know Dr. Westerling mentioned the spaghetti. So if you want to look at the actual yearly data, you can look at that as well, or you can look at it by decade. As a user, we can look at this map in a number of different ways. The map is showing us a single GCM, and we can play it to look at the animation. So if you want to start exploring different hotspots or potential hotspots within California, this is a really interesting way to start looking at the data. And you can pause it and look at it however you want. We can also search for locations. So I'm going to look at Grass Valley as a sample location. We'll zoom in. And again, what we're looking at, it's now showing me the time series data for that individual pixel. A couple other things that we can do. I'd like to point out that we have this quick stats table information. And what this is showing us is the modeled historical data and then the projected information at a particular time frame. And we're looking at, in our projections, we're looking at the average value over those 4 models and then the min and the max of those 4 models over a 30-year time period. And as a user, you can change that to really start to dig into this data a little bit more. One thing I want to do is change us to RCP 8.5, and we'll see that, you know, we actually are getting quite a significant difference in our projected average acreage burned with that. We can also change the time period that we're looking in. So back at this quick stats, I can go to, I could select my own custom year range, or I could move to end of century projections. And now we start to see some definite increase in your projected area burn over the historical range. So again, as a user, you can look at all of these different controls. You can also think about looking at different aggregation layers. For example, right now we're just looking at individual grid cells, but you could certainly look at these different layers. For example, maybe we want to look at the information for that entire county as opposed to just that grid scale. So again, we can look at these, the way all of this data interacts quickly on CalAdapt. A few other features I'd like to point out: within all of our tools, you can easily get the data in a number of different ways. So for example, if I'm just interested in perhaps showing this time series chart and putting it into a report, I can say save chart, and I just can save out this entire chart to put into a report. I can also directly save out all of the data that's used in this graph to a CSV file. And I think this is one of the really useful things with CalAdapt. So, right now it's telling me that I'm looking at a county. It's telling me my RCP, population growth scenario, business as usual. And then I'm actually getting the data for all of the models across these time periods. Again, you could look at monthly data if that's what you're interested in. So this is really handy if you want to do additional analysis or create your own charts for the data. And again, we can also look at the decadal fire probability. So all the controls are the same. This was only run on a central population growth scenario, but now the information that you're looking at is the probability that a particular grid cell will have a fire within that decade. So this is just a different way of looking at the data. And again, the information, if you would like to learn more about how we did that, you can look at the references here below. So with that, I want to really quickly show folks how to access the data itself. So if you're actually interested in, again, maybe doing your own custom analysis, or you want to extract data for a number of different grid cells, you can use our data download tool. So I clicked on data, and I'm going to go directly to our data download tool. And we have many different climate variables in CalAdapt, as everybody knows. What we want to do right now is just check out the wildfire. So we can select that. And you'll see we have two different data sets. The first one is that simulated derived product, which is the decadal wildfire model probability. And then the second data set is directly from UC Merced. So let's click on that one. You'll see that you'll get some general information, some metadata about that data set. It's telling you the variable, the scenarios that are available, the GCMs, and of course that reference to Dr. Westerling's fourth assessment paper. A couple different things. We can either access this data in a couple different ways. One thing I want to point out is that you can download the NetCDF data directly as we got it from Dr. Westerling's team. So if you're interested in really digging into the individual scenarios, you can get the NetCDF data. I'm just clicking on it to show you the amount of data that's available. So this is actually it's showing you the NetCDF data for 3 different population scenarios. And then within each of those data sets, I think is 100 different simulation runs. So if you are really interested in working with that data, feel free to grab the NetCDF and look at it that way. If you're interested in some gridded geotiff products, you can go to raster format, or if you're interested in more tabular data, you can click on the tabular format. So once again, as a user, you can select different regions of interest. One thing that I always like to point out is you can upload your own shapefiles. So if you want your own custom polygon, or if you have, say, a list of multiple points that you're trying to grab data for, you can use each of those. Right now, I'm just going to draw on the map. Whoops. It always works when I'm doing it myself. There we go. It's telling me that that feature is supported by the API. If you have a really large polygon that won't be able to process in a decent amount of time, you'll get a message about that. So now I have the wildfire simulations, and you'll see we have a large list of data sets here to look at. So we can filter this in a number of different ways. I can look at all of the 4 priority models that the wildfire data is run on, or perhaps I just want to select a specific one. I can look at either all the scenarios, so the historical, RCP 4.5 or 8.5, so we can grab all of those. Temporal resolution, this is a little interesting. So several of our data sets have daily data, but if you click on this, you'll see that we don't have any wildfire daily data. So this was run at a monthly and an annual step. I can select the monthly data. And then there's a couple other aggregations that are possible. We have additional ways of doing temporal aggregation, and I think this is really interesting. For example, maybe I'm interested in looking at the wildfire data in a seasonal way. So I want to look at the different seasons and see how that's projected to change. So I can click on that, select my data set, and then download it. This will really only take a minute. Let's see, I can save it. And then what you'll get is a CSV file that shows you, again, the acreage burned by those different months. So that's a really handy way to look at the data. I think I have it open here somewhere. Don't have it open at the moment. So a lot of different ways to access this data. And again, if you're interested in looking at the individual scenarios, as Dr. Westerling has mentioned, you can get all of that data from the NetCDF. So with that, let me know if there are any immediate questions we have about that tool. I think we're running a little bit early today, which is nice to see. If anyone does have any immediate questions, and otherwise we can jump ahead to Owen's talk.
Sure, we've got a question. This one is from Eric at OPR, who says, Nancy, will the average user understand how to contextualize area burned in hectares in comparison to the grid cell size? It could be helpful to allow viewing the data by the % of area burned in addition to raw data values. So this is a question getting at interpretation, understanding how to do something with the area burned as an example. Curious for your thoughts on that. It's also in the chat if you'd like to read the question again.
Right. That's a great question. And I actually think that Owen, I'm going to pass the buck to Owen, who I think is going to be talking a little bit more about best uses of this data. It is something that we have thought about as to whether we need to include, the acreage per the boundary layer that somebody's interested in. So if that's something that you think would be useful, it's great for us to know that. We have done quite a bit of beta testing on this tool. And that was something that did come up with 1 or 2 questions. So that's good to think about. One other thing that I do want to point out on this map while I'm looking at it, thinking about, the area and what that means, particularly over larger boundary areas, you will see that within this map, there are these gray cells. Those are, as it mentions up here, those actually are no data cells. So with the wildfire modeling for the 4th assessment, there was basically a mask put on the data where locations outside the fire, state, and federal protection areas are excluded from the wildfire simulations. So that doesn't mean that there is no fire, it just means that there's no data in these grid cells. And those grid cells are generally in areas of agriculture and urban areas. So that's also something to keep in mind as you're using this tool, that you will find that there are cells that say no data, but again, that doesn't necessarily mean that there wouldn't be potential wildfire in those areas. So hopefully that helped.
Thanks, Nancy. I do want to put out a call for folks to give us input, as Eric has just done. And there are a few different ways to do that. You're welcome to email me. You're welcome to email the support@caladapt.org email address. It's in the footer of the CalAdapt webpage and hosted in other places. You can certainly offer thoughts in the comments box here, but know that we're always looking for recommendations for how to make these tools and these data sets more useful and accessible to you. We have a question in the chat sent to me that says, will you discuss interpretation of this data and the ways that you recommend local governments use it in vulnerability assessments? And the answer is yes. In part, that will be Owen's piece next. Owen will be speaking about best practices for using wildfire projections. But I actually want to offer that question to Leroy first for your take in looking at this 4th assessment data. What are some of its strengths and some of its limitations as it might apply to a local vulnerability assessment?
Yeah, so You know, by the time these things get published, it's been many years in the making. So none of the scenarios for the fourth assessment use the 2012 to 2014 drought as their starting point. Right? So that's a difference that's quite profound in some parts of the landscape, and that's that there's been big changes in the fuels and the subsequent fire risks just based on the drought. Another thing is that there are sources of interannual variability that are quite large that are not easily captured in these models. We could incorporate them as additional scenarios, but not necessarily as something that's driven by observations, not by observations, but by realizations of climate simulations. For example, I mentioned the lightning, clustered dry lightning strikes this year, and 1987 and 2008 are examples of years in California with large numbers of fires that were ignited by lightning. And those kinds of things get smeared out in the model, right? But that doesn't mean that we capture all of the impact of them, even averaged over time, because you think about this year, for example, it's the first example we have in the historical record of that variability in lightning interacting with really extreme fire weather conditions, and fuels that have been affected by the biggest drought in 1,200 years. And when those kinds of interactions can give you sort of nonlinearities that we don't really have the data to capture. So for example, I wouldn't take 2020 and the observed area burned in 2020 and compare that to one of these average products, or even the spaghetti that the model produces, and say, hey, we're like X years ahead of schedule or something like that. You want to compare the simulation outputs for historical climate to the simulation outputs for a future projected climate, and look at those changes over time and where they're occurring, and infer from that like what's driving the increase in the model and where. But those absolute comparisons are really inappropriate for this kind of modeling. There's a question following up here saying, are you saying the lightning fire strikes aren't really in the model? Yeah, so the model is actually a suite of models, and the first layer of it is a presence or absence of a large fire of at least 1,000 acres in size. And if you look at the actual fire ignitions in the state, the vast majority of them are far smaller than that, and they're not actually caused by lightning. Most of them are caused by humans. So in any given point in space and time in the historical record, there are lots of potential ignitions typically, but only a small number of them go on to become large fires. And climate has a lot to do with whether and how those go on to become large fires. And that's really what drives the rest of our modeling, is that spread component. But the implicit in the way the model is built is that there's some underlying probability of potential ignitions, either from humans or lightning, and we capture the spatial variability in that, but not so much the temporal variability in that, the underlying implicit potential ignition. So if you had a change in lightning strike patterns or something like that, it wouldn't capture it. But also if you have that real sharp peaks in the record, right? Those get averaged out over a decade or so. So I hope that answers the question.
Thanks so much. We'll move on to the next feature presentation here, which is Owen, who's going to talk a little bit about best practices for engaging with this type of data. And then later in our conversation today, we'll start to move toward the future, looking what data is to come and what are ways to think about using it. So I see there are a few more questions in the chat, and we'll keep those afloat as we continue. So Owen, with that, all yours.
Okay, I apologize. I appear to be encountering some technical difficulties presently, but please let me know when my slides are visible.
Don't see them yet. If you want to real quick drop them in an email to me, I'm also happy to present them from my side. Let me know what's easiest.
If your slides are not open on your screen, it's not going to give you an option of sharing them.
That might be it. It appears to be some sort of permission. Can you see them now?
We got it.
Oh, great. Well, you know, when Nancy asked me to present best practices, I thought it was going to be easy and straightforward, ignoring even the technical challenges of presenting your screen. But you know, what this really gets at is how do I responsibly use complex data to answer planning and local development challenges, and what are the potential issues and catch points where you might get tripped up. So that's what I'm going to try to talk about today. And to do that, I'm going to use Nevada County as a example location. And I choose Nevada County not because I pronounce the word Nevada correctly, because I usually don't, but because the terrain is complex and ranges from sort of rolling foothills in the western part through really rigorous and complex topography and elevation gains in the center, and then you enter Tahoe National Forest, and there's Donner Lake and Truckee. So it really encompasses a nice wide range of vegetation and climate. And there's also some, you know, for Nevada County at least, densely populated regions from Grass Valley through Nevada City here, where there are lots of dwellings and where, you know, there is some fire risk. But before I get into a particular walking you through how you might use this data responsibly, I want to take a step back and talk a little bit about climate models. So climate models, the degree of uncertainty from it, the cone, the range which you must consider increases as you are trying to make more and more complex analyses. So from a foundation, climate models have to envision a future society. What's the population? How do they use energy? How do they treat their neighbors? Technology shared and those sorts of things. From which we enter the next region of uncertainty where we, from that, try to estimate, okay, given the way people are going to be living and behaving, how much fossil fuels, how much greenhouse gases are going to be emitted. Then those are passed to climate models. And in the fourth assessment, there were 32 used. And each of those has a range of possible outcomes. And then that's passed to downscaling so that we can take these large scale, more global pictures and look at them in the scales where decisions are being made. In the fourth assessment, that's LOCA. And that's what's done on what you can find on CalADAP. And today we're talking about kind of impact modeling. We're looking at, okay, taking these, you know, downscaled projections of future climate, now let's pass them to some models of, you know, wildfire occurrence, frequency, and intensity. And then let's look at that. So every time we take a step down our cascade of uncertainty, the range of outcomes increases. So I did just want to kind of make that that point early on and note that you know, we're presenting a lot of information on CalADAP, and you might be inclined to take a particular value out of it, but please note that there's a range of possible outcomes surrounding that one value. Kind of sitting on top of like the way these models are run, there's also increasing uncertainty over time. So in the top here, we're looking at, I guess, the current period where you can see there's uncertainty from behavior, and then uncertainty from models, and then what we call realizations or different individual model runs. And that's not something that the fourth assessment approach actually took into consideration. So we're kind of on the first two tiers. But over time, as we move forward, the range of possible outcomes increases. And that's a real challenge for wildfire modeling because, you know, an increase of 1 degree centigrade versus an increase of 5 degrees centigrade is huge in terms of change in the vegetation and moisture and fire potential. So two things to kind of keep in mind, that as we look at more complex issues, the uncertainty increases, and as we move out in time, our uncertainty is increasing. Nancy's already introduced the CalADAP wildfire tool, but today I will be talking, looking in Nevada County, specifically Nevada City as an example, and just wanted to sort of introduce what's expected to be happening there. You can see that CalAdapt has four of the 32 climate models with projections. We see sort of a stationary baseline period through the early 20th century, and then as warming occurs, we see an increase in fire risk in the foothills. And when we're looking at things like this, we're taking data out of an individual grid cell, and you may be very confident that, oh, that grid cell is really representing the location that I'm interested in, but that's not always the case. This is a zoom in. Here's Nevada City. Here's Grass Valley, and these grid cells that we're looking at here as sort of our baseline actually incorporate quite a large degree of variability in vegetation, topography, population density. Is it urban? Is it vegetated? Those sorts of issues. And we have seen on CalAdapt, we have seen users, come in and want to look at their house, and so they put in, okay, here's my dwelling. These blue dots represent individual buildings from the OpenStreetMap data project. And not all the buildings, but gives you a sense of where people are living and where there's lots of infrastructure. And users will come in and pick out their house or pick out a landmark in their town and wonder how fire risk is going to change for them. And looking here, if you're picking this house and you're picking this house, the answer that comes back from CalAdapt is going to be the same. That these two locations are of equal risk. But that may not exactly be true, because this house here is closer to a higher fire risk region, and more vegetated, more fire risk, and this house here is closer to the city, lower chance of burning. So I encourage people to take a sort of regional view when assessing fire risk to their community and their development. You want to understand that these models are very informative and very helpful, but they are limited. So instead of just taking one grid cell and using that as your decision-making basis, please consider the grid cells around it. We've learned over the hard way over the last few years that fires don't like to stay in their grid cells, particularly under strong wind conditions. We've seen Santa Rosa, we've seen Paradise, we've seen Ashland, we've seen conditions where fires spread very quickly. And historically, we've considered regions in developed regions to be not particularly burnable, and the models trying to reflect that, but we're starting to understand that there is risk from surrounding grid cells. So please do not just cherry pick or pick out one location, but look around to assess the real risk from wildfire. A lot of these best practices have been hinted at by both Leroy and Nancy, so I'll just go through them somewhat slowly here. But please consider more than one point. We know that wildfires impacts range from air pollution to evacuations to disruption of local economies, and an event slightly outside of your grid cell may be highly impactful to you. Look for longer periods of time. We have seen examples where people will say, I'm comparing the year 2050 to the year 1990 and showing change. And that's not really appropriate, because these models have internal natural variability, which manifests over the periods of decades, or ideally about 30-year periods. So you want to look over a wide range of years to assess risks to your community. We do hear a lot. Please give me one number to use for my planning decision making. And hopefully the slides I've shared with you today show the complexity of the information that is coming out of CalAdapt. We use runs a better picture. And as Leroy just really just said, compare model projections to historical model conditions, not observations. And that's because the models are modeling a set of understanding, slightly if you want to know how risk changing over time, apple to apple comparison, look at the historical projections. And here, hand things back to Lucy, because I think I'm approaching going over time here. But here are some ideas on how to use best practices or change your, reconsider the practices that you're currently taking.
Lovely. Thanks so much, Owen. We have a few questions floating around in the chat that we can discuss for the next few minutes before inviting David to offer his portion of today. The first question here is, let's see, from Mark up at CSU Chico, who taught class during fall 2018 when the campfire was right there. And Mark asks that when in working with his class in the data, they realized that they had predicted wildfires in their class, but the actual campfire that happened was 10 times bigger and 10 years sooner than anything projected on CalAdapt. They're using CalAdapt this semester again. And what do you suggest is sort of the message to students here about the relationship between projections and then, now that we're living in the climate change context, what's actually happening around us?
I think some of my fellow panelists will have some things to add to what I'm saying here. But I would say that 2020 and 2018 are certainly extreme years, but they could have happened now, or these sorts of compounding drought plus lightning or drought plus extreme wind conditions could happen in 2030, and they would be really reflective of the same climate period. So I'm not sure that we're 10 years ahead of schedule, but it is worth looking at maybe over the next 10 to 20, 30 years and using that as a more representative set of conditions for now than looking at just this 1 year.
Could I follow on?
Please.
So it's not just temperature that drives these, but the timing of specific drought events, for example. And the background variability in precipitation, even without climate change, is very high. And then it's getting enhanced by climate change in ways that these models don't necessarily capture. So if you think about, if you're just looking at 4 climate scenarios, for example, you're only going to have a very unrepresentative sample of droughts. And the timing of those droughts vis-a-vis the temperature trends can be really important for how the fire simulations play out. If you don't have a drought in the time period that you're looking at for your planning, you need to find one at a different time period and extrapolate from that what it would be like to have that kind of interaction between a temperature and that you're expecting or experiencing already and a really low precipitation event or a sequence of really low precipitation events in the simulation. So that drought timing or precipitation timing is really important.
Thanks to the both of you. The next question comes from Natalie Hernandez, who says, Owen, do you mind real quick explaining the future society layer again in your cascade of uncertainty? What's the nature of the uncertainty presented in that layer?
Well, if you want to hear climate scientists yelling at each other aggressively, you could ask them to debate the merits of different representative pathways moving forward. But broadly, we're moving away from the RCPs, or we have moved away from the RCPs used in the 4th assessment and the 5th assessment. There's a different mechanism, and each of these mechanisms has different projections for population, different expectations for how technology is developed and then shared between nations. Are we living in an open society where nations are freely exchanging ideas and technologies adapted rapidly, or are we living in a very competitive future? Some have really fossil fuel intensive futures, like RCP 8.5 did in the 4th assessment, and others move towards cleaner energies much quicker. And so that's really the layer that's on the top of the cascade, and then the layer beneath that is how that changes the amount of carbon that's emitted to the atmosphere, and when that carbon is emitted to the atmosphere, not only how much, but when. Hopefully that helps describe that.
Thanks, Owen. I'm also seeing a question in the chat from Janet Hatfield asking about the fifth assessment and whether it will be able to incorporate what has happened in this 2020 fire season. Things like fuel treatments, or whether work underway will not incorporate that. So I just want to say that we'll get to that a little later. Leroy will talk about the fifth assessment modeling process, where we are and what we anticipate. And so I think with that, we'll turn it over to David. I see a few other questions in the chat that I'm saving on to because I think they'll either be addressed or can be part of the conversation later. So David, all yours.
Thanks, Lucy. Lucy, can you see my presentation?
Yep. Beautiful picture of a fire.
Wonderful. I just wanted to start off by saying, Nancy, Lucy, Owen, the folks in the CalAdapt team, I'm personally really impressed by the stuff that you've been able to pull together. And we're looking forward to collaborating and sharing our data with you in the way we can. So start off with that. The stuff that you guys are producing is really amazing. The Pyregence program is an EPIC funded program, and the goal behind it is really to figure out how to build the next generation of wildfire models in an open and transparent way, in a way that allows a variety of different users to be able to access not only the data, but the analytics if they choose so. It's a consortium. It is a variety of different organizations, public and private. We try to get all the different voices that are actually dealing with wildfire modeling and the different flavors of wildfire modeling, bring everybody to an inclusive tent and have the conversations about the known knowns, the known unknowns, and see how we could try to figure out how to fill some of those gaps. The way that we've organized ourselves is we organized ourselves into 4 major working groups with a purpose-built integration that we have, that it shows it on top, but it's really within each of the different working groups, where working group 1 is led by Janice Cohen and includes folks like Owen and Andy and a wide variety of other folks. It's really a focus on trying to identify extreme weather. Where are the gaps in base research? Where are the gaps in applied research? How can we learn from that and bring that forward? I have a slide later on that describes some of the outputs that are coming out of that. Working group 2, which is led by Scott Stevens, but includes folks from the engineering group at Berkeley, also folks like John Battles, Mark Finney, and Brandon Collins, and a whole wide variety, the SALO folks. The idea there is really to get a better understanding of fuel profiles. What do they actually physically look like? How do, when you actually burn them in burn chambers, what does the fire behavior actually look like there? And if we need to get past a Rothmel-based spread model, what does that specifically look like? Work group 3 is led by Chris Lautenberger, includes folks from SIG and SALO. It's real focused on trying to figure out how to identify and predict fire spread near term, 3-5 days fire spread patterns, not only for active fires, but for fire risk across the state. And I'll show you some of the stuff that's coming out of that. And then work group 4 is led by Leroy. And when we get to that point, I'll pitch back to Leroy so he can describe all the different efforts and elements that are coming out of that larger push as well. Sound good? All right. The way that these systems are all fitting together, just to kind of give you like a bigger picture of what we're trying to do, you could think of it as a study it, build it sort of model, where the fire behavior group, Scott's group, and Janice's group, the extreme weather group, are going to give us a bunch of bits of information and information products that are actionable, that we're going to use to inform both the short-term forecasting tools and the long-term forecasting tools. And so there's an intentional integration across those different working groups, so there's co-learning occurring. Once those tools are developed and put into play, with ideas that we're going to be working with a variety of stakeholders, we are working with a variety of stakeholders to test to make sure that it's producing the types of outputs and outcomes that are actually needed and useful to them. For the forecast tools, since it is funded by the CEC, We're primarily targeting the IOUs, or the electric companies. And the idea is to be able to make it available and accessible for them to be able to use for things like PSPS or vegetation management, those sorts of things. And the long-term impact there for that track is a safe and reliable, cost-effective, resilient grid. For the scenario analysis tools, or the long-term simulations, a lot of the information that you see on CalAdapt, the idea is that it will fit into the 5th climate change assessment. And then from the climate change assessment, leveraging efforts like CalAdapt, allow policymakers to make long-term decisions that will also lead to a safe, reliable, and cost-effective, resilient grid. So if you take each of the different groups and you say, okay, well, what specifically is coming out of each of the different groups? What are some actionable things that people can actually get? So for work group 1, the extreme weather group, and Owen, feel free to correct me if I get any of this wrong. There's 4 major layers that we're trying to get into play here. Number 1 is we're really trying to take the state itself, identify major fire weather regions or zones, and then characterize the nature of fire within those zones. Where do we have the majority of surface-driven events, surface wind-driven events versus plume-driven events versus potential lightning events? And can we actually characterize that in a meaningful way and capture archetype examples of where it occurs? And where we do capture those examples, downscale it with models like coffee to actually have at least a one-way coupled model where vegetation and atmosphere, the energy from the emissions from fires getting coupled with your atmospheric models, and you have a feedback. And from that, you can select the parameterizations to run an entropy model to identify, well, where do we have blind spots from our existing network? And based on those blind spots, do we put in new facilities, or do we need to improve the facilities that we currently have using new technologies like up or air profilers to capture some of the way fire weather is changing across the state? Right, so that's study group 1. When you look at study group 2, this one's a little bit more complicated. This one really sits primarily in base research land and then approaches applied research land. It's actually trying to figure out, how do you actually characterize surface fuels? And how do you characterize surface fuels in a way that's consistent with the next generation of wildfire modeling? Getting away from a raw thermal-based approach, entering a physics-based approach, you need to build a voxelization of these sorts of characterizations. So there's a bunch of different efforts associated with that. And then the learning from the field is scaling up from the field to the state using machine learning algorithms to characterize vegetation structure. That's being led by the cellular folks. And then the configurations of those surface fuels in the field are being taken into the labs, starting at a small scale, to look at what the fire behavior actually is when you burn them. And then at a large scale out in Missoula, when you can get large configurations of fuels and you can start replicating some of these mass burning events that you saw, potentially like the Creek Fire, right? What are the configurations that actually look like? Learnings from all those different elements is going into a D1 physics-based model that we're hoping to be able to, as a module, replace some of the raw thermal-based approaches. I can get into more details here. This could suck up an hour on its own, but I'm going to pass through it real quick. Work group 3 is focused on the near-term forecast tools. Beta versions are actually up and running right now. There's a link there if you actually want to go to the site and see it. This one has 3 products that are in operations. The fire weather forecast for 3, 5, 7-day forecasts going out for all the major fire weather inputs that you need to run any sort of simulation. It has an active fire forecast, so any fire that's actually detected using some of the standard Earth observational systems, it will give you a 5-day projection of where the fire is actually going. And then it has a risk forecast mechanism, which actually runs about 500 million simulations every 6 hours to give you a statewide fire risk threat. We could show you some more of those details if you're actually interested, but all the data and the models aren't available yet. We're still in beta and making sure that they work right, but the data sets that are coming out of those models are all available on the data.pyregence.org site that you could actually see. Nancy, I hope I'm doing okay on time here. You're giving me enough. And then this is Leroy. This is where I'm going to pitch it back to you. in terms of the fourth assessment, or in terms of work group 4. Did you want to actually show this slide, or do you want to grab it back on your slide?
So I have that as my first slide for the transition. So we're good.
Okay.
I'll change the screen sharing here.
Yeah, I'll stop sharing on my side and we'll pick it up on your side.
Oh, I gotta put it up on the screen here. There we go. All right. Bear with me a second. I thought I was all prepped, and then all right. No, not that one either. What happened here? Okay. Now I'm ready to share.
What a beautiful slide. Lots of boxes.
It is a beautiful slide. Thank you, Shane. Yeah, so there's a lot of complexity here, isn't there? If you're moving from left to right, really, so we got the base inputs. So urban land use, forest management scenarios, climate variables, whether those are historical, projected, downscaled, or synthetic. So we can come up with a cookbook approach to producing test climate scenarios. We don't have to rely just on the climate models themselves. And then things that we've observed like that stay fixed or that are baselines for future modeling, like vegetation versus topography and stakeholder attributes. And then we have two different, in the second column there, two different models, dynamic vegetation land surface characterization model. So Landis 2.0 is parameterized just over the Sierra Nevada, but maybe extending up into the southern Cascades. Whereas Lucas is a state in transition model that's going to cover the whole state. So we have our statistical fire models, and we have two dynamic vegetation models, or two dynamic models that produce vegetation projections and biomass projections that can feed into the statistical fire modeling. And we actually have, some multiple approaches on the statistical fire modeling running in parallel. And so we'll be able to assess later this winter, in spring, the models separately by themselves, as well as coupled together in different configurations. And then the outputs span everything from the vegetation, biomass, above and below carbon, above and below ground carbon, to fire size, number, presence, absence, severity, and smoke emissions from those fires. And the different types of output formats. So we can have gridded map surfaces. We could have vector data, things that can flow into the CalAdapt web tool, synthesis products that, for the fifth assessment, and then a repository of code and data for people to get into the business of running these themselves. So now I'm just gonna touch on some of the issues that came up very briefly in my first presentation earlier this afternoon, and talk a bit about how those fit in. It's not just temperature that's changing, right? So as we warm up the planet, we warm up higher latitudes more rapidly than we do the equator, and that changes atmospheric circulation patterns. And one potential impact of that is a greater frequency of these patterns we've seen with bigger peaks and troughs over continental North America, and slower changing weather patterns. So those can give you setup for more extreme dry spells or more extreme wet spells, for example. And a big impact of that could potentially be an extension of the dry fuel conditions late into the year, when normally a large rainstorm would have shut down the likelihood of getting a really catastrophic fire late in the season. And here is just on the left side, modeled fuel moisture by day and by year. So each of those trajectories in the climate spaghetti there is 1 year, and the horizontal axis there is the day of the year. And you could see the campfire that did so much damage to Paradise, California. There was a real anomaly, really dry for that late in the year. And in fact, the summer where that level of fuel moisture was exceeded or similar were actually all in the last decade as well. So you can see the shift over time from blue to red there as temperatures are warming up and you're getting more evaporation. But then these departures from sort of that cloud of trajectories there, like we saw in November in 2018 for the campfire. That's more about changes in precipitation timing and how that interacts with the pickup of wind in the fall. And we've not been able to capture things like that in the previous assessments. And a big part of that is not having vector wind products that are downscaled and coming from the climate models, and reliable relative humidity estimates also coming from the climate models. And we will be working with those this time. So we have a much greater capacity to try and capture extremes in these late season fires. And as Nancy mentioned, we were masking out local fire protection responsibility areas, which were primarily agricultural or developed. But of course, we've seen that those can burn in wildfires, quite catastrophically so. And part of our charge from the Energy Commission, from the state this time, is to not have those areas masked out. And so we have to think very carefully about how to model the probability of fire spreading into those areas, and at what spatial scales is that effectively done, and what kind of variables govern that. And that's ongoing work right now for Working Group 4 for the long-term projections. Another aspect is, this season we've had both lightning ignited fires that produce really large plume dominated events in the summer, and now we're seeing wind driven fires later in the season. And I mentioned that we had also, the effects of the 2012 to 14 or more drought on fuels. So the Creek Fire, you can see there some pictures of the plume from an airplane and then from a satellite. And across the bottom there, fire progression, I think all on a single day. And typically those heat maps from a satellite would show more hotspots around the perimeter as it's burning into new fuels. And here what you're seeing is like sustained high energy production across a large area that had a lot of dead and down fuels. So that again is about this integration with the other working groups to understand how these extreme events play out in real time and what drives them, and also how to characterize those fuel changes based on the legacy of that drought. So we're working in the new simulations. The climate data are supposed to be at 3 kilometers. So about, moving from 6 kilometers now to 3, we're cutting down substantially. And then the input data are to be available hourly. So we have really characterizations now of weather and not just climate in driving these. And then we're trying to work not just at that 3 kilometer spatial resolution, but also at finer scale. So some of the dynamic vegetation modeling is done at 1 kilometer, and some is done at around 100, 150 meters. And then we're also doing statistical downscaling to 30 meters for some of the statistical fire products. So And in addition, not just modeling the area burned at those two, across those spatial scale, that range of spatial scales from 3 kilometers down to 30 meters, but the severity, so the area is burned in one severity or another. And so the sequence of modeling is really figuring out, what are the drivers, and then how does that, where and when do we get a risk of large areas burning, and then what fraction of them is, say, low, moderate, or high severity, or unburned, or pockets within a fire perimeter. And so we've been developing models that do this, not just the fire size distributions like we had in the 4th assessment, but then what fraction of them is burning at high, moderate, or low severity in particular. And then looking at what are the drivers of that, and how do we map that, again, back down to 30 meters, and how do we figure out where those high severity clusters in particular are occurring that drive the, for example, pollution emissions from fires, in particular particulates, but we're actually modeling a whole suite of emittents. So this is an example of a historical fire, the Butte Fire. And we're not showing on the left there the actual fire severities that were observed, but rather our modeled probability of burning at high severity based on the characteristics of each 30-meter pixel, and modeling, over a large selection of historic, basically all historic fires since 1984. And then on the right, we're doing this kind of analysis. So for any modeled fire perimeter with 30-meter texture of severity in it, if we're saying the probability is within a certain range for a particular severity class, what does that actually mean in practice in terms of how it relates to observations across these fires on the right there. Just a few words about the emissions. So here the shaded colors and greens and grays are showing coarse vegetation types. And the dots are the fires in the historical record from 1984 through 2016 that we've been working with. And the color, the size shows how big the fire was, and the color, how much emissions there were of fine particulates. And you'll notice that there's just a handful of really large fires that produce a lot of the historical emissions, and that are primarily burning in forest types. And just pulling out not just the biggest emitting fires from 84 to 2016, but also we've gone and modeled them for larger fires that occurred in the last few years, like the Thomas Fire or the Mendocino Complex. The 15 largest fires since 1984 account just by themselves 22% of total particulate emissions since 1984. And a very large fraction of that is coming from just a handful of very recent fires. And if we had this for this year, right, it would really be shocking how much of the particulate emissions over the last several decades occurred in this year alone. So again, on the left there, you can see our estimated emissions annualized through 2016. And if we had the last 4 years in there, it would be an even bigger spike. And then on the right there, shifting, comparing before the year 2000 to after the year 2000, you see, like, even with these limited data, that the period of time during the year when we have a lot of emissions is really expanding. And so all of that is part of what we're doing for this 5th assessment. Thank you.
Thank you, Leroy and David. We'll bring back a few questions in the chat. From Janet, says, you mentioned the work for these products taking years. Will the 5th assessment be able to incorporate the 2020 fire season fuels treatment, or have we passed that window of opportunity? And I think more broadly, it's a chance to say, does 2020 plug into a lot of this future-looking modeling? If it does, how? If it doesn't, what are your thoughts there?
I'd like to think that we could. So the statewide land surface modeling, vegetation modeling, carbon modeling, everything that was being done by the Lucas Group, so Ben Sleater and company, they're actually using the historical fire perimeters, and so far, I think through 2016. So instead of simulated fires, they're using, for all the larger fires, the actual observed fires from the Monitoring Trends and Burn Severity database, and actually slightly modified by us. And I'm hopeful that we can figure out a way to bring that at least through 2000 and have that be 2020 and have that be our baseline. Because I don't want to be in a situation like we are with the fourth assessment where we weren't able to incorporate the effects of the 2012-2014 drought into it, and that was such a transformational event for thinking about future fire risk. I'd like to think that we might be able to incorporate 2020 as well. We just haven't, nailed that down, whether we can make that commitment yet or not.
In general, what is the timeline for this consortium work?
Well, the climate, downscale climate projections, correct me if I'm wrong here, David, are not supposed to be available until 2024?
Yeah, so it depends on the work group. So for the near-term forecast products, those are out right now. They're in beta, they're operating. The long-term forecast, since it has a lot more moving pieces and there's some external dependencies that we have, we're still trying to negotiate how to get those to work out well. But there are some, yeah, it's going to take, we'll get the near-term stuff out first, and then the longer-term stuff will come out right after that.
There are, data constraints where our final product, our final deliverables depend on data that we don't control, that we're not producing ourselves. But that's not preventing us from moving forward. So we've identified similar alternative data sets to use for model development, and then for model testing, again, we're going to generate our own sort of artificial climate scenarios and use them to challenge the models and test them and understand how they behave under extreme conditions. So I think we'll be in good shape to then port everything over to whatever final baselines and projections that the state wants us to use.
Yeah, I mean, it would be horrible if we released a bunch of test data just because we're trying to test out the pipes and how they work, and have to retract it all to put out the official data set. It's just, we want to be careful with that. But if people are interested in learning more, we do have open doors. We're happy to have conversations and happy to share what we have with folks, including our approaches in the science. We encourage the conversations. Yeah.
Next question is from Eric at OPR, who says, what coordination is taking place with CAL FIRE's FRAP team on updating fire hazard severity zone mapping to account for climate projections? How is this engaging CAL FIRE?
So we have a technical advisory committee that's part of this program, and we have we meet with them very often, and so they're abreast of what we're actually doing, and we spend a lot of our time trying to coordinate our efforts with their efforts. We also have some sister projects and programs with them that are complementary to these existing projects, where we're trying to take all the different efforts and trying to do some air traffic control with CAL FIRE. So we do have constant conversation with them on these sorts of things. I don't know, Leroy, if you wanted to add anything to that.
Yeah, there's that Center for Ecosystem Climate Solutions. They're focused more on doing a nowcast. So what is the fire risk right now? How to best characterize that? And the models that we're using for Pyregence also will feed into part of that product. So that'll provide a comparison of, a touchstone for the present or the near future versus these projections. And then actually there's another project with CAL FIRE here in California, just starting up this winter, that some of us are participating in, that is focusing particularly on the Sierras. And so again, a lot of the same modeling technology is going to flow into that, but using, for example, the climate models from the fourth assessment, because the climate models that we're going to be using for the 5th assessment won't be ready in time. So there's sort of going to be intermediate transitional products that are going into some of these applications. So we are working directly with CAL FIRE, some of their concerns.
And that's true for all the different models too. So we have these long-term climatological forecast models, and we also have these more short-term physics-based or optimal-based models. It's the same sort of relationship where we're trying to build in both approaches for the appropriate questions at the appropriate scales, and trying to learn between them. And those conversations are occurring with CAL FIRE. They're also occurring with the California Public Utility Commission and a wide variety of other state organizations. But happy to have conversations with anybody else. So if you're not included, please reach out. We're happy to share.
Good to hear that there's an open door policy. Last question in the 1 minute that remains before I wrap things up here. Many folks reach out to the CalAdapt team to say, I appreciate the data is available. What resources do you have for me in using it in hazard mitigation planning and climate change adaptation planning? So I'm curious to know, if folks come to you with that question, where do you point them? What are resources to think about climate change adaptation as it relates to wildfire?
Yeah, it's really a capacity question. So, for example, I showed you some of the work we did for San Mateo County. They actually spent $1 million over 12 to 18 months to do their assessment for their region, and it was very labor intensive because we had to curate, things individually for them. So that's part of the work that we're doing for the assessment, is really to think about how we can develop and build in some additional tools that would automate some of that and allow counties that don't have $1 million to spend grant money to sort of localize scenarios for themselves. Yeah.
We are here at time, so I just want to say thank you to everybody for coming. And I actually have a few recommendations that you check out a few resources. One is the California Adaptation Clearinghouse. The link is resilientca.org. The Adaptation Planning Guideline 2.0 is soon to be released from the Office of Planning and Research. That's another great resource. And then lastly, Eric, whose name has been popping up in the chat, Eric DeCock at OPR, also has a lot to say, and so may be able to support you with technical assistance and guidelines. So thank you for coming. It's been a pleasure sharing this time with you and thinking about wildfire. And feel free to be in touch. We'll publish this recording on the CalAdapt website and on our YouTube channel if you would like to share it with anybody else.
Great, thank you everybody for joining us. Especially thank you to Leroy, Owen, David. It was really great to get that information on wildfire modeling, the state of the art and the next generation. So thanks so much. We really appreciate it. Thank you.
Thank you. Bye.